So I got 0 over 1. Oh my god. The look he just gave me brought a tear to my eye. Do you see it?
Yeah, I do, yeah. All right, let's go ahead and check in. So remember, we had a whole bunch of information in that first unit on limits, but a lot of it boiled down to some strategies. I'm going to shut this, my goodness. Various strategies in algebra. Algebra has kind of been a 4-letter word for us this year, so I'm hoping that we'll just keep improving those skills and like those just inherent understandings of what can and can't be done. Looking at the first one, number 7, what would be your first strategy? Did anybody check if it's indeterminate first? Okay. So check that, right? So maybe start by saying, is it indeterminate? All right, anyway, yes, you're right, it is. So let's factor, and let's be real aware of notation. That was something we worked hard on after the test. I think we kind of saw that was an issue, so hopefully it's getting better. Do I need to write limit next? Like if I'm going to chain some equals signs, yeah. Yeah, what does this factor to be?
Can I try? I got x plus 1 times x plus 1/3. I did the quadratic formula and I don't know if I did it right.
Oh, okay. So the third won't work in there.
Wait, would it be 3x plus 1 then?
Yeah, there you go. Do you guys know the star method? It's quick. Or versions like that, like bottoms up, guess and check, that kind of stuff. Factors of 3 that add up to 4 are just 1 and 3. Okay, and then before you go stick it back into your factors, you need to reduce. So this becomes 1 over 1. And then our two factors are 3x plus 1 and x plus 1. Now here's a little hint. Often the denominator, or at least maybe part of it, the denominator, will be one of the factors of the numerator. If that helps, you can kind of use that. Now you do want to make sure, don't just assume that, but sometimes that saves you time. All right, anyway. Clearly there's something that cancels, and oh my goodness, chill out thing. Okay, and then what do we do? Like, I'm going to put it down here just to keep it from going off the page. Do I still write limit? It depends, right? Like, if you want to show the simplified function, then yeah, you need to write limit. Then you can just say equals what?
-3, -1 plus 1.
So -2. Okay. That kind of got a little bit messy right there. So factoring, that was a big strategy. How'd that go? Like the problem, the limit problem. Oh, good. All right, next one is a limit as x goes to infinity. What kind of function is this? If we just took off the limit and we're not thinking a calculus context. Yeah. It's that kind. What was it called? It's not specifically a reciprocal, but it's similar. Starts with an R. A different R word. It's rational, right? So if we're looking at the limit as x goes to infinity, what are we really looking for? So go deeper than just, can I find the limit, right?
Big over big or big over small?
Yeah, but I'm talking about like a description of what this will give us. Yeah, called a? Which kind?
Horizontal.
This is looking at the horizontal asymptote. So what will this function do as we go out far to the right.
Go to 9/2.
Okay. Now, let's do this analysis in terms of calculus. You guys are hyped up today.
I had a very exciting meeting at lunch.
Well, I guess that's good. So, just to review, because a lot of you are falling back on that algebra understanding, right? Which is, oh, it's the same power or same degree, so we just take the coefficients, and that's okay, but I want you to know how to do infinite limits because not all the questions are about horizontal asymptotes, are they? Right? So what matters as we look far to the right? That's really what this is asking. And so what does matter? Can we do that algebraically? What we just did, we dropped off the 4 and the x. Can we do that algebraically? Only if we evaluate a limit as x goes to infinity. Otherwise, you can't just drop things off. It's not like we can just take our eraser and ignore it, right? Only if you're writing this limit out front does the -4 and the -x become insignificant. So here's what I'm saying to you actually. If you went and wrote this on your paper and you stuck an equal sign, it's not true. It's wrong. Because algebraically, those are not equivalent, are they? So make sure that that notation isn't just there because somebody stuck it there. It has very definite purpose. Okay, but because those are the same, those two x squareds, now we can cancel them and say that the limit is 9/2. Now we don't need the limit out front anymore. We can just say that it's 9/2. Okay? Be careful with your all this stuff is equivalent or equal, because that can get you in trouble. How about this next one?
Same, I got that.
It is determinate.
Yeah, this one is indeterminate. Sorry, is not indeterminate, so we don't need to worry, right? Just plug that right there. And what do I write after the equals? Do I put limit as x approaches 0 again? Why? I plugged it in, right? So this is now sine of 0 over 0 plus 1, which is 0 over 1, which is 0. Okay. How is that for a little review? Do you okay on it? Okay. I'll keep putting some of that kind of stuff out there. Any questions on the homework? Can you chill? Just bring it down a little. Questions on those 4 problems? You guys are checking your answers, right?
Yes.
Getting feedback? Okay.
At first it seemed really hard, but then it got really easy. So
Okay, good. Oh, I stuck that in the wrong spot.
here we could have been back.
Yeah, just go. I don't want to take time to do that. All right, let's go ahead and finish those notes then. Just a reminder, we're differentiating inverse functions, which that involves a little bit of memorization of the structure of our derivative. Anybody have it memorized yet? Like if I just said, don't look and write it down? Just one of you? Here's one tool that I don't remember if I mentioned, but I'm going to now. Write it down every time. Every time you do a problem, it will help you memorize. Anyway, so you guys did some practice on this, but let's just continue. So number 4, are we good to just jump right in, or do we need to sort of talk through some of it? Are we okay? Okay. All right, number 4 then, if f of x is defined as 3x cubed plus 1, and g is the inverse of f, what is the value of g prime of 25? So these are kind of like the ones you did, but we'll just use it as kind of a review. I would start by writing g equals f inverse some version of that. Is that an official part of your answer? No. It's just helping you to keep track of what to plug in and where. So that means G prime is d dx f inverse, which is 1 over f prime f inverse of x. Okay, a couple things on this one. Let's go ahead and we kind of got it set up, and of course we'll end up plugging 25 in for x, but note that we don't know any of the pieces in here. Do you know what I mean by that? Hello. Huh? Oh, well, since you walked in, that reminds me. None of you guys have paid for your AP tests, and you have a deadline coming up. So, the 8th of November. It's like 3 weeks. Yeah. So, get on it.
Yeah, you'll go onto that total registration, put in your information, and you choose your test, you choose your teacher, and then it'll have you put in your credit card. That's it.
Does it have to be online?
Yep. If you have something specific that you're questioning, just send me an email or come to the front office and ask, and I'll help sort it out for you, okay?
Yeah. And I handed everybody out that paper, but if you need it again, I can email it to you. Okay? I think I still have one. Yeah. So I'll do that. But let me know. Either email me and I'll email you back, or just tell me after class and I'll write it down. But we got to get that paid for, guys.
Not a single person.
Not a single one of you.
Those guys,
I know. All right, back to this note. We don't know the inverse or f prime, either one of these. So how do we get them?
We can solve for them.
Okay, let's do that. So f inverse. How do we do that?
Switch X and Y and
Yeah. Goodness. All right. Now I will. Well, let's go ahead and do this just as a review. How do we get y back by itself again? Just talk me through it.
-1 divided by 3 cube root.
Writer's on fire over there. Good job.
Wonderful.
Okay. So really what we're after is f inverse of 25, right? So to plug it in, like we're looking for this. Now we have actually the inverse function. But let's go ahead and plug that in. So cube root of 25 minus 1 all over 3. Chloe, what do you got there? Okay. Good job. All right, so go ahead and put that up. Let me remind you of something I told you on Tuesday. Get your structure set up and then see what that tells you need to go figure out. Like sometimes we know F inverse, like the ones like this one. We could just look at what was given and figure out the inverse. But set up your structure, meaning write this down and then realize, hey, I don't have the inverse. I also don't have the derivative. And then you can go plug those in as needed. But that way you don't get lost in where things go. Okay, I also don't have the derivative of f. So let's go put that in here as well. So f prime of x is what? How about you, Pedro?
9x squared.
Yep, just 9x squared. Okay, so that is f prime. And now we need to stick 25 into that. So for now, I'm just going to write f prime of 2. And I'm running out of room. So I'm going to go right up here. And we're going to say 1 over. Do you see at this point why it's so easy to lose the 1 over? Because we've had to go do a lot of other work. Right? And it's like, oh, shoot. So that's why I say set up the structure first. So this is 1 over 9 times 2 squared, which is 1/36. Sorry, I kind of got it off the screen there. Any questions on that? Okay, let's make that little note, just in case you go back to this, which I think you should. Set up the structure. Then find and fill in. I'm going to say it that way. Okay. Use structure. Structures help. Structures are what we learn. All right, next. Are we good on this stuff now? Like, do we feel good about that? Can we move on to the next section? Huh? Oh, brother.
Please.
You know what? I think I'll pause here. Let's take time to do the test prep. Just see how that goes. I'll probably give you a few more problems, but let's see how the test prep goes. Maybe take 10 minutes, then we'll check it. Okay, functions f and g are differentiable. I do kind of want to use this real quick as a review. What has to be true for that to be true? Yeah, Devin. First, it has to be continuous. Which means we're talking like no discontinuity. So no jumps, no holes, no asymptotes, like continuous, right? Devin, what else? Or were you done? Okay.
No corners or cusps.
Okay.
Back to Devin.
What else? You forgot one. Yeah, say it.
I said I'm past vertical.
No, it's not vertical asymptote.
Dude, listen to me. Vertical lines. You can't go straight up and down. That's right.
Do you want to say it? No vertical tangent lines.
Dude, if you just say what I tell you.
Okay. Now, how do we know, thinking piecewise functions, how do we know if the derivative, I'm about to say it, if it's differentiable? I almost said the actual thing. So piecewise, right? You have two pieces, like some piece, maybe it's three pieces, and we're saying maybe this is like x is less than or equal to 2, and then this is x is greater than 2 or something. What do we check at 2 to know that if it's differentiable or not? First, check continuity. How? Limits from both sides. Equals, let's just say f of a. Okay, and then how do we know if it's differentiable? You guys aren't getting this review. Like, pay attention. Make sure you know this. Like, this should come out of you almost as much as me, right? Meaning, I can stand here and tell you it. If you're doing your job, you should almost be able to tell me the same thing. Okay? So, how do we know, thinking piecewise, how do we know it doesn't have a corner, a cusp, or a vertical tangent? Set derivatives equal, right? All right, now we don't have to do all that in this, but it's just good to think back like, oh, if I have to solve for A and B, suppose, like that kind. Remember that kind? That's what we did. We said, okay, let's get a continuity equation by setting the pieces equal. In fact, let me put that on here. i.e. set the pieces equal. Then we took the derivatives of both and we got a differentiable equation. So and then we use that system to solve for A and B. Remember that? If you're like, what? I don't remember that at all. Go back and check your it was Unit 2 differentiability stuff. I can't remember exactly what section. Anyway, so the table below gives values of the functions and their first derivatives, and h is f of g of x minus 6. So first, why must there be a value r between 1 and 3 such that h of r equals negative 5? Well, what do we know for sure since we just said the thing said differentiable? All right, so h is continuous. I'm going to word it a little bit more technical than that. Is a continuous composite of two differentiable functions. Okay. Composite, meaning we're combining f and g. And what else? Did anybody do f of g of x? F of g of 3, f of g of 1. We need to put that on here, right? So f of g of 3. Or you could start with 1. I'm just picking 3. Okay, how do we do that with the table like this? Go ahead. All right, so what's g of 3? G of 3 is 4. So this is f of 4, which is negative 1. Okay, and then let's do f of g of 1. I'm going to go down, actually, which is f of 2, which equals 9. Thank you. Yeah, so minus 6 equals negative 7, minus 6 equals 3. Okay, is the requested value between those two? Yep. Okay, so we can say h of r equals negative 5, not positive, is between h of 3 and h of 1. Now we've met all the conditions of the IVT, but they're very explicitly shown, right? So there's no messing around, like trying to hope that we got it. So we can say according to the IVT, how do you finish that off? According to the IVT, nope, we can't just say the point exists. We need to be a little bit more technical. Guys, nobody knows how to word this?
We can just draw it out. Or I don't think we could say it.
Just say it. According to the intermediate value theorem, what?
There is a value between h of, 3, well, h of 1 then greater than h of r and greater than h of 3.
No, because where is r? We're talking about r, not h of r, right?
Okay, then it would be just 1 greater than.
There you go.
Yeah.
There is a value r, and then we can say r is between 1 and 3,
And then we do the h's, right?
such that h of r equals negative 5. That's all. Okay? Huh? Well, good job. Okay, if g to the negative 1, so inverse g is the inverse of g. It's kind of weird wording. Write an equation for the line tangent to the graph of y equals inverse g of x at x equals 2. Whoa. How do you do that? What's our structure for tangent lines? Let's start there. All right, so obviously we need y1 and x1 and m, right? How do we get those? Oh, you're right. We use the table. Okay, let's go back to the problem, though. It's the statement, I mean. If g to the negative 1 is the inverse function of g, so are we doing h in this case? Like, we just got done doing a whole bunch with h. Are we still thinking h for this one? Okay, so we have to like peel back now and go just looking at g. So we're writing the equation for y equals the inverse function of g of x. So at x equals 2 means what? Means I'm going to put a blank for g inverse. What does x equals 2 mean for g inverse? Remember we switched those, right? Okay. So if we say g is 2, x is 2, what is inverse? What is the y? I'm saying it wrong. That means that's a y, and so what's our x actually? Yeah, that's the y. So we're looking here and here, of course, but we need to know which way to plug them in. So what goes in for y1? 1, 2, 1, 2. Which one's the y coordinate for g inverse?
2.
1. Okay? Guys, remember I told you yesterday, or whatever day it was? Go up there and switch those for g inverse, right? And just write it up above. Like these are the x's, those are the y's for g inverse. It's backwards. I think that's helpful. So don't forget that little strategy. Anyway, how do we get the slope?
Wait, I had that.
Oh, okay.
The new formula.
Okay. I love how much room we get to work on these. So m equals d dx g inverse of x, which is 1 over g prime g inverse of x, where x is 2. I'm going to go ahead and fill that 2 in, actually, just because I'm running out of room. Okay, what's g inverse of 2? It's 1. Okay, what's g prime of 1? It's 5. G prime of 1 is 5. Okay, so our slope is 1/5. And I'm just going to drop that in right there. Did anybody get that one? 1, 2, 3, 4, 5. Okay, 6. Good. All right, last one. Function h satisfies h of 3 equals 5, h prime of 3 equals 7. Which of the following statements about the inverse of h must be true? All right. Now, this is that notation that I was talking about that I personally don't like. It's kind of weird to put the prime and the inverse at the same time. But note that it will come up, and it just, if you put parentheses around the inverse part, it helps. Anyway, what was your guys' answer on that? What? D? Is that what you said? B? D? It is D. How many of you got it? Just so I know if we need to do it. Okay. I'm happy with that. Hey, he's back. Yep.
Please, this is a requirement from Mr. Hayward. Please take the panorama survey.
Oh, she can't get in. She doesn't have a Chromebook, and we tried, and she couldn't figure out how to log in.
No one's computer will let her in?
Oh, well, I guess you could borrow somebody else's.
Here's one right here. Come on over.
She's going to miss calculus for that thing.
Mr. Atkinson, can I sign you out?
Uh,
So she can sign it?
yeah.
Cool.
Seriously.
Yeah, you gotta do, we're at 50%.
Dang.
Part of the, this is part of the big picture thing.
Yeah. All right, we're going to move on, so just go ahead. All right, grab your paper and flip to 3-4.
Mr. Atkinson, may
Huh? Oh, yeah. Okay, this, if you look at this page, it looks a little bit complicated, doesn't it?
Thank you, and sorry for the interruption.
Thanks. Like lots of stuff going on here. This is all memorization, at least this first part. And as we've been doing, we're going to say memorize. I'm sorry. Okay. Okay. This, please, I don't know if you guys have highlighters or colors, but just maybe make note of this. You might have this told to you in all these different ways. So arc, remember, is the same as inverse for these trig functions. Have you guys ever seen that in pre-calc? Did you ever see arc in front? Some old calculators say arc, maybe even not so old ones. In other words, like inverse sine can be written arc sine, and same with all the other 6 or the other 5 trig functions. So just don't panic if you see that on an AP question, like, oh, what the heck is arc? It just means inverse, okay? So there's a sort of pattern here to these, but, well, there is a pattern. Don't scribble these out. I'm just going to do it for now. Don't worry about those 2 or those 3 on the right. You're going to see the pattern really come out on those. If you know these first 3, you can get those others really easily. So I'll tell you that. Okay, here's a couple of strategies. If it has an S, it's going to have 2 things in it. One is going to be a subtraction, and the other is going to be a square root. Okay, so S, subtraction, square root. What? What is funny? Okay.
If it has an S or if it starts with an S?
If it starts with an S. Yeah. Because, he's saying, cosine, but it'll have that too. So you could say it either way. Both of these have 1 over, and they're going to have a square root. It's not working. Well, here, click on that.
Here?
Yeah, class link. Just click class link. Let's see if we can do it this way. Yep. Hold on. Apparently this is of utmost importance. So. All right, and then scroll till you see it's like a big blue P. There it is. Right, is that performance matter? That's not it, sorry. Does it have a P? Do you guys remember? Panorama? We could just search for it. Okay. Oh, don't do that. It's getting you in there. Okay. There you go. All right, anyway, let's get back to this. So, they're both going to have a minus. And in this case, it's going to be 1 minus x squared inside of that radical. And on the bottom one, it's the other, or the second one, I should say, it's the other way. So x squared minus 1. So just reverse the order. Now, I left a little spot out here in front on the second one. So the derivative of the inverse secant has absolute value of x out front. Okay? It looks kind of ugly, doesn't it? Yeah.
It looks very ugly.
Yeah. Okay, bottom. Similar, only there's no s, so there's no square root. There's no s, so there's no subtraction. So this is just 1 over x squared plus 1. Or you could do 1 plus x squared. The order there doesn't matter. Okay, again, these are inverse trig functions. What is an inverse trig function in the first place? Like, what does inverse sine even mean? Let's make sure we're clear on that.
It like lets you find the degree with an input.
Except for we never do degrees in calculus, but you're on the right track. So it lets you find the radians from the, what?
Ratio?
The ratio, like root 3 over 2 or whatever, right? So that's what these are all doing, is telling us an angle from a known ratio of side lengths, if you think of it that way, okay?
So it's like sine of y.
Yeah. Maybe it would help if we put a number to it. If I said this, what is the inverse sine of 1/2? Let's just go with that one. So inverse sine of 1/2. Start using your unit circle real quick.
Oh, it says it.
What was it? Nobody knows? Where does the sine ratio equal 1/2? That's what we're asking. On the unit circle, where does the sine ratio equal 1/2? Pi over 6. Where else? 5 pi over 6. So if you're thinking like unit circle, pi over 6, and then right over here right before pi, right? So 5 pi over 6. And then how about down here, like 7 pi over 6?
No,
Why not?
it's negative.
That's negative. How about 11 pi over 6?
Also,
Also negative, okay? But that's what's hard about these, is you have to think about all the places where it takes on the values, okay? But that's what an inverse sine does, or inverse trig function does, is spits back the angle for a given ratio. Everybody clear what we're doing? Okay. So it kind of speaks a little to why these are so messy. All right, here's the good news. Do you remember the rule if it has a c in it? Remember when we did derivatives of trig functions? What was the rule when we had a c?
It's negative.
Yeah, so just make that note. If it has a c, it is negative. That's why I said it's easy to get these ones, because we'll just go put a negative out front of our derivatives. Now, I'm not saying they're any cleaner. They're still nasty looking. But just make that one negative, and then you'll have your all your complementary. Did you know that that's what the CO stands for? What is complementary?
It fills in the rest so equals 0.
No.
Well, I don't.
What does complementary mean in math?
It fills
Like,
in the rest to equal 1.
nope. Means it adds up to, like, for these kind of things, it's the complement of 90 if we're doing degrees, right? Remember complementary angles? 30, 60, 90, right? So 30 and 60 are complementary. They add up to that third, right? So like cosine is complement of sine, basically. Cotangent, complementary tangent. Okay. Are we good on that? Do you have them memorized yet?
no. You're a liar, Devin.
Okay. Just a quick reminder. If it has an s, it's got a radical, a square root, and a subtraction. Notice all four of these with s's have that. For sine, the 1 comes first. For secant, the x squared comes first. And then it's the same over there. With secant is kind of ugly. So think I've got to add ugly in front. I don't know if this is helping, but that's kind of some strategies for memorization. Okay? Find the derivative. Let's go ahead and do these examples. So d dx inverse sine of 3x. Uh-oh, what's going on in that one? I'm saying now we're getting towards the end of our derivative rules. So what's all going on in that one? Chain rule, because we have a function inside of a function. So we need to work with chain rule and also the derivative of an inverse trig function. Okay? What do we do first? What do you mean by that? Well, you could maybe, I don't know, do this du times dv dx or something. I don't know, that doesn't usually help you guys. So what do you mean by set it up? Sorry. Sure, I'll give you a sec. Time's up. And maybe you kind of just do it inherently and I just don't get what you're saying, but
Why would we give him a sec? I have something to say.
you do, huh? What else is new?
Next week, I'm the hire kids to come play free during this time. Don't forget to say I bet.
All right. Next time they do that, I'm going to. All right, so this is inverse sine. Let's see if this is what you meant. And so we know it's 1 over the square root of what? Try not to look. Start building those memory muscles. 1 minus what? 3x. In parentheses, please, because it's not just x that's being squared, it's both. So 1 over square root of 1 minus 3x squared. That's the first part, or the outer function, and then times the derivative of the inner function, which is times 3. Okay? Now you could bring the 3 over. And, okay, quick algebra check. Actually, let me write this first. 9x squared. Okay. So all I did was just square that. Okay. So quick algebra check. Is this the same as 1 minus 3x? In other words, can I square root those and just write it as 1 minus 3x to clean it up a little bit? No way. No way. Okay? Don't do it. Why? Why do we have to just leave it like that? To what? Take the root? Is that what you said? He's kind of right. It's because we have the subtraction sign, right? So it's an order of operations thing. I have to work out what's inside before I can root it. You can't just piecewise, like, take square roots of stuff. You can't cherry pick like that. So it's kind of what he said. And since we can't do 1 minus 9x squared, then it has to just stay in there like that. All right, you guys, let's do this next one. Do we see chain rule again? Do we see chain rule? Okay. So what's the derivative of inverse tangent? What's the derivative of inverse tangent? put it in parentheses, 2x squared squared plus 1
Plus 1.
times
4.
4x, the derivative of the inside. Okay, kind of clean up. What does 2x squared squared become?
2x cubed. 4.
4x to the fourth. Okay, how about this? I'm zooming in. Those cancel, that cancels that, makes it a 3. So this is actually 1 over x cubed plus 1. Is that okay? No, that's not okay. But can you see people making that mistake? Do we all agree Manny might do that?
I mean, he was writing it down, so I thought that was correct.
No. You can't do that. Again, why?
Because
Because of the addition. Yep, the addition.
Sometimes I wish we had like those dividers from elementary school, so we
Let's just hide behind it.
can look.
Okay, what the heck? What does this mean?
That just means derivative. Come on now.
No, it doesn't. It doesn't mean derivative.
That means inverse. Inverse.
Okay. Hey, by the way, notice, just for notation's sake, it's because we don't have enough room to go to the right, but I'm putting equals in front of this because, like, normally if I had enough room on paper, I would say equals and do it here. But we need to say, like, where is this coming from? In other words, if I just start writing, it looks a little weird, doesn't it? So this equals the next word. That's all. It's just, this is all crammed together so you can't go to the right with it. Okay, what's the derivative of arc secant? Try not to look. It has an S, so we know it has what? Square root and subtraction. For secant, which comes first? The x squared or the 1? X squared. So, I'll move that over. So 5x, whole thing squared. Wouldn't that be an annoying way to mess this up? If you forgot your parentheses and you only squared the x, right? So use those parentheses for any chain rule stuff. Okay, what goes out front? 5x, yeah, absolute value of 5x. And then times our chain rule, which is 5. Let me just write that into a 5. Okay. You'll notice the next section is simplifying the secants, the inverse secant derivatives, because we kind of look at this and think, hey, is there a way that we could simplify that 5 since everything in the denominator is being multiplied, right? And there are ones that are more messy than that. So let's kind of talk through that. In fact, number 4. Just to make sure you're clear, this is already a derivative. In other words, we took the derivative to get there. So now we just are looking at simplifying it. So maybe make sure that stands out. We're just trying to simplify that. And then we'll go back and finish number 3 after we talk through this. But here's what the kind of general idea is. Simplify as usual first. But then we have to check some things because of the absolute value. So then check, and I'm going to say what that is in a second. But what can we simplify here to start? Like pretend the absolute value is not there. What could you simplify? All right, so this 3 and this 9 become 3 on top in the numerator. How about the x's? Okay, so the x squared cancels 2 of the x's in the denominator. So let's rewrite. So this would be 3x. Let's see if I can make that a little less heavy. Over x. And then don't simplify anything inside the square root.
How is the x still on top?
It should just be 3.
Yeah, you're right.
Good catch.
Oh, come on. Why does it do that? Okay. Anyway, this x sitting out front came out of an absolute value, right? Okay. So I'm going to write a note off to the side. This x came out of absolute value. So we need to verify if it needs it again. In other words, do we put it back on there or not? That's the question. Okay? Well, it's not just, we have to check stuff. We're always going to check x equals -1 or whatever variable, but try -1 in there. Okay? What happens if I plug -1 in to this blue version, the simplified version? What happens to the sign of the whole thing? Yeah. Okay, so I'm going to write that over here. If we plug in x equals -1, this is negative. But in the original case, was it negative?
Yeah.
So you just have to make sure it stays the same as the original.
Yeah, okay, that's a great way to say it. This is negative, or originally it was positive. In other words, if you plug -1 up here, do you see how that is positive? Right? If I plug -1 for x there, -1 squared is positive. It would be positive over positive. But for this one, it's +3 over negative, which is not the same. Okay, so we need absolute value on the x to make sure that it stays, the whole thing stays positive. Remember, all we're doing is simplifying. We're not like plugging in. We're not changing anything else. We're just simplifying. Like think of reducing fractions. But if we're going to reduce fractions, we can't change their value. Does that make sense? Okay, so I'm going to finish this note. So we need absolute value on the x. So it looks a little simpler. Do you agree? I mean, it's better. Okay, let's look to the next one. This is already a derivative. Simplifying as usual. What can be simplified in this case?
4 and 2.
Okay, that 4 becomes a 2. That 2 cancels. That x and that squared cancel, right? And so we're left with 2 over x square root of 4x squared minus 1. Okay, again. Plugging x equals -1. Originally, what sign do we have? So up here, if I plug -1 here, the numerator is negative. -1 down here, the denominator is positive. Right? Negative over positive makes the whole thing what? Here, let's write it out that way. Gives negative over positive, which equals negative. Okay? Plugging x equals -1 here gives positive over negative, which is negative. So do we need an absolute value? So we don't need absolute value of x. And it's because these two match, right? So these are the same. So we don't need, so in other words, we can, the purple thing I wrote, it's okay. We don't need to put absolute value on it. Yeah, Pedro.
If you like put an absolute value on something even if it doesn't need it, like that, you know?
Yes, that's bad.
So think about it more and don't think about it as much from an FRQ standpoint, but more from an MCQ. Like what if the best answer is this, right? Or what if out of the 4 choices, maybe this is the only one that actually is right and the other ones have absolute values but are wrong somehow else? You know what I mean? Like maybe there's another thing that's wrong, but it has the absolute value. So if you haven't gone this far, this one might look wrong too. Does that make sense now? I would worry about this more from picking answers out of a list than doing it on FRQs. Okay. We could go back to this one and say, like, into the original. Original, it was positive over positive. Versus positive over negative. Okay, I'm just adding kind of what we did. These don't match. Just to remind you kind of how we checked. Okay, last stuff. Almost last stuff. Guys, all of that wasn't derivatives. That was just simplifying. But just know that you'll need to be able to do that in order to match answers potentially. Okay? All right. These are kind of interesting. Do you remember the definition of a function? Like, let's do a quick, easy Algebra 2 example. Is that a function? Is this a function? No. So we have to have one output for each input, right? Okay. Well, these inverse trig functions, like we just said, actually just going right back up here, I have one input and 2 outputs. Do you see that? That if I just say the domain is wide open, that's not a function because I have 2 outputs for this 1/2. That's my input. Okay? And the unit circle kind of illustrates that based on the one we just did. Don't write this, just think about it. Both of the, I guess I missed it a little bit. There we go. Both of those have a input of 1/2. In this case, our input is up here, right? We're doing inverse. And now we have 2 angle values for that. So anyway, we have to restrict our domain so that it actually stays a function. So those came back. Put this note out to the side. We must restrict the domain to assure it's a function. All right, if you have a highlighter, it's kind of nice, but for the inverse sign, that's our domain. So we're restricting to the first and the fourth quadrants. And you can read it there. The range is negative pi over 2 to pi over 2. That's our output values, right? Our outputs are now the angles, not the ratios. Let's make this quick note, like a sub note to this. We need a positive and negative quadrant for each of these. What does the graph of sine look like? If you want just a quick background on why this is, the sine of x graph starts at 0 and it oscillates, right? And then it does the same thing this way. So what does the inverse graph look like? Now it goes this way, right? Okay, so we have to limit this to just one little segment of that is kind of the idea. Oh, that's the wrong tool. Like that, right? Top half. I kind of missed it there. There we go. Just that little piece is what we're doing. Otherwise, do you see how it cycles back and now we're no longer a function? But if we just cut right there to right there, it never repeats. It never has a secondary output value. Are we good with that? Okay. So this is what we're talking about when we say negative 1 to 1. Okay. Cosine. Can you predict which way this is going to go? Where's our domain for cosine? Well, I'm asking you that. Well, it already says it. But for a similar reason, that's our domain for cosine. Okay? The tangent graph is interesting, huh? What does the tangent graph look like? Yeah, like we have, remember this kind of shape? Remember that? Where are those little hashtag marks? Do you remember? Like where does pi over, or I almost said it, but where does tangent have vertical asymptotes? Pi over 2 because the denominator is 0, right? Sine over cosine, it's wherever cosine is 0. So pi over 2 and negative pi over 2 and any multiple of that, okay? I feel like I'm not connecting, but the inverse tangent graph just flips that on its side. Okay, so this one is now like that. Sorry, I flipped it the wrong way. Okay. So what's our domain? Well, do you see how it goes on infinitely? Left and right. But now our range is restricted. So we just flip that, domain and range. Okay. All right. So this one again is negative pi over 2 to pi over 2. Same thing. Same thing as sine. All right, last thing, really fast. We kind of did this. What is arc sine at x equals root 3 over 2? This has to be on the domain now. Oh, come on. So remember we're saying arc sine of root 3 over 2. These are not derivatives. This is just like run-of-the-mill trig stuff. So what angle gives us a sine value of root 3 over 2? Pi over 3. Now, is that in the domain? Yeah. Do we need to worry about going down to the fourth quadrant? No, because that would be negative root 3 over 2. All right. What is inverse cosine of negative 2 over 4? Well, that's the same as negative 1/2. So what value, where do we have a negative 1/2 cosine value? Remember, cosine's domain is on the top half of our unit circle. So where does it have a negative 1/2? 2 pi over 3. Okay? On the left, good. All right, so that's all those are. All right, for tonight, do the odds and test prep, and we will check on that tomorrow.
Do we have your class tomorrow?
You do, yeah.
Let's go!